Okay, we've been working our way through Bodhi plots, actually the whole technique called frequency response, where we're looking at uh, the response of a system as we subject it to a, a whole variety of sine waves, and we want to see what the magnitude ratio is of our input to our output, and then what our phase shift is from our input to our output. Ideally, what we would like is for to have a magnitude ratio of 1 and a phase shift of 0. And then our output would be mimicking our input exactly. But what we see is that with any real system, we see a fall off and some resonance and a whole variety of things coming in play as we increase our frequency. And so our task as control engineers is to try to assess how hard we can drive the system, and then design controllers to improve the response of the system. And so we've been looking at primarily at a tool called the Bodhi plot, where we're plotting the response, magnitude and phase for these frequencies. And we've looked and hopefully understanding now a little bit of how these tools, our tools, work within the Bodhi plot. We have three tools: gains, zeros, and poles, that we can put into our controller and hopefully shift the Bodhi plot to a more advantageous configuration. The gain causes the magnitude plot to shift up or down. With the zero, we can shift the slope of the line in the magnitude plot up, thereby shifting it and the phase. And with the pole, we can shift it down, the slope down. So we can alter the Bodhi plot somewhat with our poles and zeros. So that's where we're headed in this section, is trying to understand what it is that we're doing and then how to implement a controller to the best advantage. We're going to be using a technique called loop shaping to do that. Before we get into that, though, I want to talk a little bit about stability. Of course, in the root locus method, stability was very easy to assess. If we had closed loop poles in the right half plane, we had an unstable system. There wasn't a whole lot of ambiguity about it. And we could also see if a system was going to go unstable by looking at the branches. If the branches even were in the left half plane, but then as we increased the gain, they moved into the right half plane, we knew that there was a limit to the amount of gain that we could put into the system. And so stability was was fairly obvious in the root locus system, and that's one of the reasons that we like it. But the Bodhi plot isn't quite as obvious as to where the system goes unstable. But we do have some tools, and that's what we want to talk about today, is gain margin and phase margin. These are two tools that we can use to assess. So let me bring up some notes here, and we'll start talking about this. The stability criteria, as I said, is the gain margin and phase margin. And these are a couple of tools that show us the safety margin. Okay, this is akin to walking up to the edge of a cliff. How close do you want to get to the edge? Now, interestingly enough, most of the time our performance of the system improves the closer we get to the edge of the cliff. But if we get too close, then we run the risk of stepping off and going unstable. And so we want to think about these margins as a measure of how close we are to this disaster. The margin is of the safety between you and this big disaster. And so we want this positive space. Now remember, we always want our phase margins to be positive. And so we're going to be talking about a positive phase margin, a positive gain margin. And then if we get a negative, you're unstable. And so that's where we don't want to go. So these are a bit interesting and a bit counterintuitive also as to how we get them and where they come from. So here we've got a couple of plots, open loop, and remember, we're going to be working on the open loop on this to control the closed loop stability. But we're going to be looking at the open loop. And for the loop shaping, we're going to be looking at the open loop also. So we've got the open loop. Now, let's talk about where these margins come from. Physically, they come from the idea, or come from a couple of points on here. To get the phase margin, we're going to look at this point in here. I'm going to be working with the red first, the red line. These are actually two different magnitude plots. I'm going to be looking at the this point in here, where it crosses over the 0 dB line, where our magnitude plot crosses over the 0 dB line. All right, so now we have a great and novel name for that point. It's called the crossover frequency. It's where the magnitude plot crosses over. Okay, so we're going to go from the crossover frequency, and we're going to move down. Okay, down into the phase plot, and we're going to look at this frequency in here. Now, it is this distance here that tells us the magnitude of the phase margin. Okay, the magnitude of the phase margin. And we can see the actual calculations on this. In this case, we have a positive phase margin, and so we would actually calculate this from our 180 up. And so this distance in here is our phase margin. Okay, and it's measured in degrees, and we definitely want it to be positive to have a stable system. And if you want to calculate it, you can use this little equation here that I highlighted. The phase margin is the phase. In this case, it'd be 85 degrees, or minus 85 degrees plus 180. So that would get us something around 95 degrees as our phase margin. Or you simply can go from the minus 180 phase and go up to your phase plot line, and that is the phase margin, so it would be 95 degrees. Okay, so that's the phase margin. We get it from the crossover frequency on our magnitude plot. Okay, and this is a little counterintuitive. We've got to watch out for that. So then, let's talk about the gain margin. The gain margin comes from the frequency where we have a zero, or the crossing of our minus 180. Okay, so we're looking at this point right here, the minus 180, and then we're going to go up in here, and we're going to look at the phase margin as our distance from our phase plot to, or I'm sorry, our magnitude plot to the 0 dB line. So this would be our gain margin for that red line in there. Okay, and in this case, you can just identify it as the negative of the gain. In this case, we've got a gain of let's call it minus 25 dB, and so our gain margin would be 25 dB, and so that would tell us we have a positive gain margin. So this system, characterized by the red line through here in the magnitude plot, would be a stable system. Got a positive phase margin and a positive gain margin. Now, if we add some gain to the system, okay, and remember, our gain will shift our magnitude plot up. So if our gain goes up, our magnitude plot goes up, and what we would end up with then is the plot by our blue line. And in that case, our phase margin would be characterized by this point here. Remember our zero, our crossover frequency, and our phase margin would be down here. In this case, we've got a negative phase margin, okay? And we see also, as we come up here, from our phase crossing the minus 180, we get a negative gain margin also. And so by shifting that magnitude plot up, by increasing our gain, we've driven the system unstable. And we can tell that by negative gain margin, negative phase margin. And so that's where what we want to do with these margins is use them to assess the stability of our system. Okay, so let's see, let's look on down here, and there's yeah, okay. Again, just emphasize, we want positive gain margin, positive neg margin. We want to avoid negative gain margin, negative phase margin. And many times we can adjust these by the gain. The gain, remember, slides that magnitude plot up and down on our Bode plot, and we can make that happen. Let me shift over here to a MATLAB, and here I'm running SisoTool, and so we can I've put in just a simple 3-pole system. Okay, we've got a couple of poles here on the real axis, 3 poles on the real axis. 2 of them are going to come together, split, and move in this direction, and then the third one is going to go out on our negative real axis. Okay, so so here we see we've got our closed loop poles from our root locus. We see they're in the right half plane, and our step response indicates that we've got a nice stable system response here. And if we look over here to our Bode plot and see what's going on with this is the open loop Bode. We see this GM right in here is our gain margin, and it's at 325 dB. Okay, and our phase margin is infinite. So we've got a really, really good phase margin, gain margin in here. Very stable system. But we've also got a pretty slow system. We've got a response about 1.5 seconds to a settling time in here. So let's see if we can improve this. Now I'm going to grab the Bode in here, and I'm going to start lifting it up. Okay, and if you watch the gain, we'll see that the gain is moving. The gain right over here. We see the gain is moving in here, and we see our closed loop poles move around a little bit, and we improved it a little bit. Let's shift it up some more. Too much. Let's put it back down here. There we go. Somewhere like in there, and we've improved our performance a bit. But we see our gain margin has been reduced to 41 dB, and we're still at an infinite phase margin. So let's see if we can shift this up just a little bit more. Put it up a little bit more. Okay, let's go there. Let this settle out, and we see now we see from our root locus we've moved the closed loop poles out quite a bit. We've caused a lot of oscillation in here now. Okay, we still have a stable system. We can look at our root locus, and we see all our poles are still in the left half plane, so we're stable. And we can validate that also with our gain margin at 6 dB and our phase margin at 26 degrees. And so Incidentally, they're plotted on here, right in here and right in here. And so we still have a stable system, but we're starting to pick up a lot of oscillation in here. Now, if I continue to increase the gain on this, we can take it up into this region. And what we'll find is that by increasing that gain, we've driven it unstable, and we end up with a negative gain margin and a negative phase margin. And so we get a good correlation in here between the phase margin, gain margin, and what we observe on the root locus, and then the response of the system. And so that's how we assess stability in the frequency domain, or in the frequency response method, is the gain margin, phase margin of the system. Tells us whether the system is going to be stable or not.